All right. Today is the first. Okay. Today is the 4th of January, fourth day of January, January 4th, 2026. We have to remember that the year has changed. I want to thank everybody for coming today and participating during the year 2025. Okay. There's Ian. Still don't see Roger. Okay,
If
well,
you
I guess, huh? I
if
started the
you
re
arrange your icons to the right side of your screen, you'll probably get the best view of the screen I'm sharing.
well, thank you for that. Let's see. Okay, so I guess you can go ahead. I did mention the issue that I might disappear during the presentation yesterday during the 10 o'clock. The my internet went out, which was some kind of a surprise to me. So if I disappear, that'll be the explanation. All right.
Well, we will all be mourning if you disappear.
Well, that wouldn't be. I don't plan on. I'm not planning on it. Okay, so you can go ahead and get started. You're going to talk about binary mechanics cosmology,
Yes,
um,
sir.
and you've sort of modified. You're changing some of your ideas based on what previous discussions, and that's my understanding of it. Is that correct?
Well, actually, I think it's basically similar material, but better presented. I presented this material in the form of a video previously, and the link for the video is here in the paper. And so hopefully this is a much better presentation and more succinct.
Okay, go right ahead.
Okay, well, first, what is binary mechanics? Um, Basically, all of the theories that we have that are popular in theoretical physics these days is based upon the many thousand-year-old assumption that space and time are continuous. What binary mechanics did was to quantify and space, time, and energy. And so that this is a completely different approach. And one reward for this different set of axioms, which I call full quantization, has been that we've been able to derive all of the basic constants of nature, the vacuum speed of light, Planck's constant, electron risk mass, elementary charge, and so forth, only from first principles without using any other unexplained measurements. Because these so-called fundamental constants are considered, prior to binary mechanics, unexplained measurements. Now they're explained. So with that general global introduction, let me continue. The objective is to create the universe in today's talk from the equations of a theory of everything known as binary mechanics. Binary mechanics equations and results of the binary mechanics lab simulator, which is a free download. You can get it with the link right here. This is a paper on my website, binarymechanics.blogspot.com. The premise here, this binary mechanics lab simulator implements the equations of binary mechanics, and it'll be used to create a fully functional universe. This is the only cosmology that I know of that from its first principles you can create a fully functional universe. The premise here is that the most complete and comprehensive physical model is the essential starting point for a viable cosmology. And of course, you all will be the judge. After a brief background, the best cosmological model is built step by step in today's presentation. And as I said, it's based upon the video linked here. So here's my little illustration. Best theory of everything is a requirement to have the best cosmological model. One paragraph of background. Binary mechanics was developed from antiquated 20th century quantum mechanics by adding the postulates of full quantization of energy, space, and time. Results from the old quantum mechanics could only give a probability for a physical event obtained from a complex number called the amplitude, shown in figure 1. Now, in this figure, I've parsed the amplitude. Normally, you just have x plus the I, the imaginary number I, y. I parsed it, parsed x into what its sign is and what its absolute value is, and the same thing for y. Now, we quantized energy. This is just a very brief background so you understand what's to come later. If we limit the absolute value of x and the absolute value of y to 0 or 1, we've quantized energy. And with the quantization of space, we're going to say that we're going to basically postulate that these two energy items, which are binary numbers, they can only be 1 or 0. And they're designated as the L bit, which is represented by arrows, and the M bit. And if we house these in a physical object called the spot unit, each with their own cube of size L, which is the basic fundamental length constant in binary mechanics, we can put 3 of them together and form what we call a spot. The spot is just where 3 of these spot units are assembled into a structure which exists in space. If we combine these spots and take into account that there are 8 permutations in the parsing of this complex amplitude that are possible, we get actually 8 different particle types, which are arranged in a spot cube, which is the matter particles, are the electron, which is in yellow here, and the 3 d quarks or down quarks in the dark red, green, and blue, and the antimatter particles, again, 3 down quarks with the light red, green, and blue. There's a light green, light blue, and light red. And the positron, which is not shown because it's on the other side of where the electron is shown here. Let me see if I can use the arrow keys. Yes, I can. The parts of this complex amplitude can be parsed to quantize energy, as I just said, by limiting the absolute value of x and the absolute value of y to 0 or 1 to get binary mechanic equations 1, which m equals 0 or 1 and L equals 0 or 1. When m or L equal 1, the bit locus is in the 1 state called a quanta of energy. So we're just getting some vocabulary here under our belts. Hence, there are 2 kinds of energy defined in binary mechanics, designated M and L with length quantized in the italic L above, forming a spatial object called the spot unit. And L, as I mentioned, is the primary length constant in binary mechanics and is approximately 2/3 femtometers. Okay, 3, yes, someone. Oh, that was somebody sneezing. Okay.
That's all, yes. Thank you.
God bless. Okay. 3 spot units may be combined in 3D space to form a spot, as shown above in the figure. There are 8 permutations of the parts of the complex amplitude shown in the upper left, which define the spot cube, which predicts 8 elementary particles, 3 down or d quarks, the electron, and that's 4 of them, and their antiparticles, 4 more. Finally, space contains the latest of these spot cubes. Okay, which is
I do
very,
pardon the interruption, but can I ask you why 0.67 centimeters? I didn't catch that.
that was derived from the what I call the secondary constants, which are the speed of light, what are commonly known as the so-called fundamental constants, which are really before binary mechanics, which are really unexplained measurements. Okay, so that's where the 2/3 femtometers comes from. And there's a whole paper on deriving these values called How the Primary and Secondary Constants are can be derived. Okay, now there's the spot unit. Finally, space contains the latest of these spot cubes. In other words, space is not empty. The entire universe has this lattice, okay? And this with that short introduction, let's go. Let's do this. We're ready to create a universe. First, we need a place to put things. Step one is that we need this place to put things. That place is the spot unit. The things are the one states called quanta. Let us agree that the universe consists of things at locations. If we can just get that far in agreement, we're in good shape. At present, binary mechanics allows people to think what they want concerning what the things actually are, okay? Because note that in what I said above in this very brief background about binary mechanics, we have one states and zero states, and that's rather abstract thinking. But by binary mechanics at present just asserts that each of these two loci in the spot unit may be in the one state or the zero state. So if we can agree and get that far, we're in very good shape to start building our universe. Now, the spot unit is actually a machine. It's not just a place to put things. The spot unit is more than a volume. What things do we have? We have the L and M type quanta, which represent units of energy. In addition, the spot unit must contain parts needed to implement the time evolution laws, including the bit operations in the binary mechanic equations 7 through 17. Figure 2 shows 4 configurations of these hypothetical parts. And let's motor on down to that. Okay, we had not shown in the figure above the E plus right-handed particle is the positron, and it's a lepton. There's 2 leptons here at the top, and we have a certain arrangement of parts which are shown in different colors here. And we notice that the spot units have these parts configured in this way in the positron spot. In the electron spot shown in yellow above, the parts are arranged differently. So this is just the purpose of this figure is to show you that really the elementary particles may not be as elementary as one might think, because actually there are only 4 types of spot units, which is a more parsimony than what you get with considering the elementary particles, of which there are 8. These parts might include guides, valves, and sensors. So the different colors shown above here could be guides, valves, or sensors. A guide are simply a barrier that prevents motion of quanta through a spot unit wall. Valves allow passage of quanta in only one direction. Sensors are needed because neighboring little cubes in the spot units act as potentials. And so that we're going to need sensors to determine the state of neighboring loci. For example, one states in those loci represent potentials, as I just mentioned, the scalar, electrostatic, and the vector or magnetic bit operations in the time evolution laws. The 8 elementary particles in the spot cube consist of 4 types of variations of these parts in their spot units. And so really, it could be the most fundamental physics possible in today's world is what are the parts needed to make the spot units function as little devices or machines to implement the equations of binary mechanics. Okay, now where do we get angular momentum in the universe? One of the very first things I did with the binary mechanics simulator back in, I think it was 2011, was to populate the simulated volume with one single quanta. And guess what I discovered? It's not in the equations. If you look at the equations and go down, you wouldn't even think of this probably, or at least I didn't. What I found is that if you just run the simulator with that one quanta, remember there could be millions of quanta in the one state in a simulation, but let's say we just establish only one site as in the one state. What happens when you run the simulator is that it moves around and returns to its original position. What the hell? That was the discovery of the fundamental basis for observed angular momentum in the universe. And it was provided, as I mentioned, in 2011 discovery of intrinsic angular momentum in the proton and electron bit cycles. So the first question I asked was, how many bit cycles are there? It turns out there's only two. Now, one thing in this picture here, you might get a better feel for what I'm talking about with the spot cube lattice. Here I showed two spot cubes together in this illustration. Imagine the whole universe is a lattice of these things, okay? Above, to the right, behind there, and to the left down here, and so forth. Now, the electron bit cycle is what I call it. Is shown by the purple circle here. The M bits are represented in all of my illustrations as little circles, and the L bits, or the L quanta, are another type of energy which are represented by arrows and which actually represent momentum. Now, if we just set one of these to 1, as I mentioned above, we'll observe that it moves around in a circle and returns to its original position, and will continue to do that forever until some sort of event will cause the one state quanta to move on out to another spot and eventually to another electron spot over here. The gray point here is the axis of rotation, and it's really the solid diagonal between the electron spot and the positron spot, which is shown on the other side. And we'll see it in further illustrations down below. So back to the question, I'm not even rereading anymore. I'm just presenting it perhaps in a more fluid way here. Of how many bit cycles do we have? Does the red D quark here have its own bit cycle, or what? It turns out that if we start with a single one state quanta in other locations other than the electron spot, we discover the proton bit cycle. And guess what? The proton bit cycle includes all of the locations which are not included in the electron bit cycle. In other words, there are only 2 bit cycles in this universe. Another very interesting thing is, by the way, if you have charge rotating, as shown by the purple arrow and circle here, that would create a magnetic effect in conventional classical physics. And so it's interesting that to notice that the proton bit cycle revolves around in the opposite direction. Now, let me take an inventory here and see if I've covered what I wanted to cover here. So what we have done now is we have the most fundamental possible origin or mechanism or understanding, if you will, of what why there is any angular momentum whatsoever in what we observe in the universe, that galaxies rotate, the Earth rotates around its axis, it also rotates around the sun, all of this angular momentum everywhere. Okay, shown in figure 3, I think I talked about that. They exhibit rotation in opposite directions. Yeah, I talked about that. So let's move right along. The electron and proton bit cycles are important discoveries to better understand. Now, in other words, if you take away from my talk today that we have a little better understanding of cosmology than we did before, I'm happy. Okay, we're not saying that, and I don't think anyone can say we have the full story ever. For example, I just stated above, we really don't know exactly what a guide or a valve or a sensor is, which I'm hypothesizing to be parts of the spot unit. And they're probably more than the 4 parts. For example, a state indicator is the locus in a 1 state or a 0 state. So you see, there's a whole lot more to understand. So if we can better understand things, we're way ahead of the game. Okay. Now, let's see, let me use the arrow keys, better. Okay. A previous detailed account of motion mechanisms provides frame-by-frame steps involved in all particle motion to build our universe. Once we have some particles, we have to understand how they move and whether they move or not. Okay, and so we're going to delve into this in a lot more detail as we move along here this morning. Knowledge of how particle move is required. Prior to binary mechanics, theories such as Newton's motion laws were satisfied to describe motion, leaving the mechanism of particle motion for another day. Biologists seem to have more curiosity than many physicists. Biologists were not content to describe the velocity or acceleration of a cockroach on a table. Okay, we're all done. We know how fast the cockroach moves. We can tell you when he accelerates or when he stops, which is deceleration. So we're done. We're finished with physics. Biologists said, no way. We want to know. And they wanted to discover and know the contractile proteins causing a roach leg to move. The physicists have to catch up with the biologists. The energy source in the ATP, that's adenosine triphosphate molecule, the neural networks coordinating the muscle contractions. So the corresponding gaps. So the biologists have filled in a lot of the gaps in how the cockroach moves around the table. But and binary mechanics, I think, provides a lot of information concerning the gaps which exist in if we only have Newton's motion laws. In physics, the binary mechanics description of the mechanism of particle motion is not just a bonus perk. Okay, you say, oh, wonderful. That's a nice little add-on to put that arrow into our quiver. It is rather an essential part of the story on how the universe works. If we can't even tell you or even suggest how an object moves and what the mechanisms are, we're way behind in the game. Or if you want to inverse that statement, binary mechanics is way ahead in the game because it has a description of how particles move. Now, we're doing pretty well here, but there's a lot more that we need. For example, complexity and variability. The universe cannot be a boring place. Okay, let's agree. It can't be boring. So we need a lot of complexity and variability. There are 6 quantum locations in the electron spot, as I showed above. And each locus could be in a 1 state or a 0 state. Hopefully we've understood that much. Thus, there are 2 to the 6th power possibilities, which is 64 different configurations of the electron. So that's a little bit of complexity. That's not bad. And that that gives us some variability, even without considering the configurations, excuse me, of spots near the electron in the spot cube lattice. Now let's go to the pro version of the bit cycle. Here we have, let's see, if I click this, oh yes, this is a wonderful, I'm using Chrome for this display. Here is the pro version, okay, that arrow going clockwise, the large black arrow in the previous illustration here is shown in this depiction of the proton bit cycle. Now, this is the pro version, okay? Just for the general public, we'll give them a simple version that we had before, but you all are pros. So, you know, we're going to give you the pro version actually for free. You know, there won't be any extra charge. So what do we have here? One spot unit is going to have an M-type locus, which can have a plus or minus charge, and an L-type locus shown in arrows in other illustrations, which can be pointing one direction or the other, so that a pair of these is a spot unit, okay? And there are 42 locations here. Now, I'm showing this in roughly the same angle as you see here, where the red, dark red is matter quark, is upper left, blue, dark blue is upper right, and green at the bottom. And so we have here green, the dark green at the bottom. And this is supposed to be light green, but it doesn't really, it's a little bit lighter. Our dark red is upper left, just like in the other illustration. So I've shown this more or less at the same angle. Now, with 2 to the 42 locations, which could be in 1 or 0 state, we have a whole boatload of complexity. So suddenly we all can just go out and celebrate because, wow, this means our universe has a lot of variability and is a very, very interesting place. Now, one thing you notice I'm showing this at the more or less the same angle as I showed the spot cube, and there are 2 of them here in this lattice. Now you notice that there are 4 locations which are actually 2 spot units, excuse me, 3 locations outside the spot cube, outside what I call the home spot cube for a proton bit cycle. And there's one of them. It's outside. Up above, there's another one, a pair, again, 1 spot unit. And the gray is our positron spot, a spot unit in the positron spot. Here's gray down here outside the home spot unit. And to the lower right, again, gray spot unit, this pair here, and a light blue antimatter, again, spot unit. You notice all the ones that are outside the home spot cube are all antimatter spot units or spot units in what we would call in conventional physics the home spot cube. So we got a lot of complexity there. Now let's see if I can go back. And here we are. Okay. Now I should be able to arrow down. Now, I don't want to repeat myself, but I think this paragraph here, pretty much I've said everything here, allows energy of the proton bit cycle to venture into neighboring spot cubes, which is an important factor in nucleogenesis. So start thinking about this, Ito, okay? Now let's go to the motion law. Another discovery of binary mechanics, which comes from the basic postulates of full quantization, okay, was the motion law. And I'll call it the Keene motion law just so we can designate it with some name other than saying motion law. Because then you're going to ask, well, which one? Well, the Keene one. With knowledge of how things move, which we discussed above, I didn't explain it all, but I referenced it, so you can look into that. Here is the reference, 6. A new law of motion can be added to how the universe works. Namely, objects move toward higher energy density, all else being equal. In other words, if there's some other object coming in colliding with Earth, Earth is going to move because of that collision, and that's other things other than this Keene motion law. But if all else is equal, we have the motion law. And what is it? If we have a higher energy density, which could be quanta of radiation, for example, if our object here is above 0 Kelvin, it has a temperature above absolute 0 Kelvin, it'll be radiating quanta in infrared and perhaps other bandwidths as well, and it's going to have a high energy density. Now, the object may have a lower energy density on the other side. Let's say this object is the Earth. On the side that faces the sun, its energy density is always going to be higher than the other side, which is not receiving direct sunlight. And the Earth is rotating, so the exact place on Earth's surface where the sunlight is shining is going to be changing in a 24-hour cycle, as we all know. But at any moment in time, approximately 1/2 of the surface area of the Earth will be receiving this radiation from the sun. And by the way, that would be a cause of radiation pressure to push the object away from the sun. But on the side facing the sun, it will have a higher energy density compared to the dark side of the Earth at any moment in time. So we can then define an energy density gradient. And it's just subtract the two densities and divide by the diameter of the object or size of the object. And so that we can then come up with a motion law force to place this in the kind of rubric or concept that we find in Newtonian mechanics, where we like to talk about forces and what is the force of this or that. So the Keene motion law force equation would be this here. And this all works out with the proper units. In other words, the displacement of one quanta through an area A would be this amount of force. And so I think I've explained the text here pretty much completely, so that you see the energy density gradient may also be considered to be a vector pointing to the direction of motion. This motion law may apply at all scales. The object could be a single proton or a whole planet, a whole galaxy or group of galaxies. The motion law may be expressed as a force with displacement dx of one quanta through an area A times the energy density gradient. Okay, let's see. I better use the arrows here. Planet distance from the sun. Now, before Newton's universal law of gravity, it was pretty much agreed that mass had nothing to do with the phenomena of gravity. In other words, the famous Tower of Pisa, a Pisa type experiment where you drop two objects of different weights and they arrive down to the Earth and bang down on the ground at the same time. Everyone seemed to agree that really mass has nothing to do with it. However, Newton said, the hell with that. We're going to say it all has to do with mass. And that, of course, was rather unfortunate because now it turns out that mass is generally correlated with the diameter and hence the energy density gradient of an object. And so that this kind of correlation masked or hid or made it seem plausible that the mass of the object was a central ingredient in the phenomena, in gravitational phenomena. But as it turns out, then when this universal gravitational law was applied to the whole universe, this correlation breaks down, because it's not a matter of, one planet, an aggregated mass such as the Earth. When we consider the whole universe, we have dispersed galaxies, and within the galaxies, the objects are also dispersed with vast areas of low density space between them. And so Newton's law completely broke down, and you get about a 10x error. In other words, that 10x error was used to define dark matter, which is about 4 times more dark matter, supposedly, than the actual luminous mass, which is about 4.5 or whatever percent, and the dark matter is maybe, let's say it's 45%. So that's a 10x error, and that error shows up because the mass is distributed all over the place and not concentrated in one compact object like the Earth. And so you see Newton's law goes right out the window. And rather than saying we have a 10x error in Newton's law, they said, no, Newton's, we'll stick with Newton's law, and we'll just say that there's some matter, but it's dark, and we don't know what it is. But Newton, of course, was right. And so,
Okay, well, we got like 2 minutes. So this would, before you go on to the next section, maybe we ought to just pause here.
okay, that's a good idea.
Are you
Thank
done
you,
with this section, or do you want to, or not?
Let me just do this one paragraph. Planet distance from the sun is mostly determined by 2 factors in the binary mechanics scenario. First, radiation pressure from the sun pushes a planet away from the sun. This is acknowledged by astronomers and is used to calculate trajectories. Second, the Keene motion law moves a planet towards the sun, since the planet energy density vector is always pointing toward the sun, as I described above. So this is a whole new way to look at planetary orbits, and how far a planet is from the sun, without considering the mass of the object at all, period. And I'll wait to the next section. And I'm about halfway through here, or maybe 45% through.
I proposed a question in the chat for the group. Would everybody be willing to throw Harry $20 or $30 so that he could get a proper Zoom account, so we don't have to deal with these stops? I'm in for 30 if you want.
What stops is he talking about?
These
He's
pauses.
talking about the 40-minute time limit. I would rather discuss that at another time. So,
Okay.
Jim, do you? So we got less than a minute here before it's, so we're done. I think this idea of getting rid of, you've talked here about, when you talk about your law of motion, you sort of jumped into, a real controversial subject here. They're really holding on to Newton's law, despite the fact that rotation. Okay, we're back. What I was saying is that I see physicists are going to want to hold on to Newton's law as long as they can.
Yes, I think you're right. I'm trying to share my screen now. Let's see. Do I have to give a request here, or?
Yes. And I'm not sure.
Okay,
All right,
I've done that, sir.
Okay, my comment is that you kind of jumped along from you're covering a lot of ground very quickly. We start off with the bit cycles and the spot cube, and then now we're talking about Newton's law of motion. That's kind of a large leap.
Yeah, well, we've got a whole universe to create. So,
And we're only going to do it in a short period of time. Okay, move on. Good going.
but I think we'll get through it. I might be done, and there'll be plenty of time for questions and discussion, and disagreement or agreement or whatever. Should I continue now, Harry?
Okay, matter aggregation.
Yeah. Oh, okay. This is just an illustration about how the motion law might work. It acts to aggregate quanta into spatially separated objects. Now, this is what we observe in the universe, okay? So if we're going to create a universe from the first principles of binary mechanics and its equations, we have to get the universe that we actually see. In other words, it has to be a data-based presentation. This aggregation effect occurs at all scales, from single electrons, protons, atoms, and molecules to solar systems and galaxies. So let's look at this illustration here. Okay, this figure 7 here illustrates the idea of showing two spatial dimensions. We've got close, far, and right, left, and the mountain height represents quanta density. Okay, so our third dimension here, which is height, is going to be quanta density, as if this were some kind of a 3D graph. Okay, now the red arrows show the direction of motion due to the Keene motion law. So here we see objects will tend to move toward the peak. And they're moving up the hills, which up the hills means toward higher quanta density up the peak. And you notice, if we consider these two arrows here, what we have is this arrow shows objects, or you can think galaxies, whole galaxies moving toward this direction. And therefore, there's a separated space between the two galaxies, between the galaxies of this red arrow, which gives you a dispersion of galaxies. So that was the purpose of this illustration, hopefully to make it a little bit more intuitive. This motion towards two different peaks, as I said, leaves a volume of lower density between the peaks. This effect results in a grouping of galaxies and vast regions populated with fewer galaxies. Now, guess what? That's, as far as I know, and I'm not an astronomer, but it seems to be that that's the way that's the universe that we have. So binary mechanics is hitting the ball out of the park so far. We're getting the universe that we actually have. The action of the motion law leads to a potential problem. Eventually, if you really want to think out to the future, the universe would come together into one giant mass of energy. Now that would be a problem. Excuse me. This problem is solved or offset by mechanisms which disperse concentrated energy, jets and explosions. Extreme energy aggregation due to the motion law may result in massive jets of quanta from central galaxy volumes, something which apparently has been observed, and explosions, massive explosions, such as supernovas in volumes with near maximum energy density. Results from the binary mechanics simulation software confirm energy dispersion role of explosions. Okay, in figure 8, how am I going to do this? Okay, let me read this. In figure 8, we only see part of it here. We'll get down to the whole thing, but we have the initial quanta density for a simulation, excuse me, may start with very few quanta on the left. When you see the whole thing, here is very, very few one states, in other words, an almost empty volume. And on the right, a high quanta density up to maximum. This is a concept that we get in binary mechanics. There has to be a maximum energy density. Since any one locus can only be in the one state or the zero state, you can't have two one states in one single locus, in other words. We've quantized all that. When the simulator runs in vacuum mode, this is what I call it, All the quanta that leave the simulated volume are lost to the simulation. They are just gone. These quanta represent electromagnetic radiation and kinetic energy of particles, in my opinion, in the simulated volume. The temperature of the simulated volume is reduced to 0 Kelvin. This we can't do on Earth because no matter how we try to cool things down, we can get close to 0 Kelvin, but the Earth is moving and motion is going to create some heat, and there you go. So we never can get in the lab, but with the simulator, we can actually reduce the volume to 0 Kelvin. How do we know we have that? For a period of time running the simulator, no further quanta exit the simulated volume. And so that if we wait long enough, I mean, light travels rather fast, electromagnetic radiation. So, and we should see it exit the volume. Well, if we run the simulator long enough, we see there's nothing comes out. There's no more particle motion, which can collide with the boundaries of the simulated volume and therefore be lost. And so that's how we know we got down to 0 Kelvin. That's an important point to understand. When there is nothing left to exit, what remains is at 0 Kelvin in the absolute reference frame provided by the simulator. By the way, Roger Anderton was asking me about the two-way speed of light and so forth in a previous episode here. And what he may not have understood is that those light speed measurements, which I presented then, were actually in the absolute reference frame provided by the simulator. Okay, now let's go down to the figure here and see what we can see. Here's our supernova. If we start with maximum energy, you see it's up to 1. You can't get any higher. For our initial density, what we have here, at the final density, once we've cooled down to 0, is very low. This result right here, and to a lesser extent here and here, represents a massive explosion. Okay, and so we have actual results from the binary mechanics lab simulator for a supernova type event. A massive explosion, and the density in the remaining volume is so low, it's actually below the proton threshold, the threshold for creating a proton. And in other words, we're really talking about causing huge volumes of almost empty spot cube lattice, or what we call empty space, but binary mechanics is telling us that space actually consists of this lattice that I described. Now, what is these two curves? If we take out, well, here's the final density observed. If we calculate the number of particles and how much quanta are required for those particles to exist, the pink or reddish curve here shows what the number of quanta in the vacuum. In other words, the so-called vacuum is actually teeming with quanta. In fact, most of the energy in the vacuum is, most of the energy in any volume, well, I shouldn't say any volume, but let's say right here on Earth in our laboratories, most of the energy is in the vacuum and not in the particles. That's what this figure is showing you, and the giant explosion here off to the right. I can come back to this figure if there are questions on understanding this. I think I've discussed this. Oh, okay. In fact, most of the energy in the simulation at 0 Kelvin is not particles, but is one-state quanta, as I mentioned. Circling, this is important, circling in bit cycles for the proton and the electron, okay? But below the threshold for particle formation. In physics, this is often referred to as the C, or the virtual C, or virtual particle C, which particle physicists like to talk about. Here, the binary mechanics simulator actually can quantify important parameters about this virtual particle C and actually define it quite specifically. And the threshold for particle formation turns out to be 3 quanta per elementary particle spot in order to have a particle detectable by our instruments. Okay, consider the result when the initial density is maximum. When cooled down, this is a summary of what I just said for this figure in figure 8. When cooled down, the final density is very low, below the proton threshold. This indicates a massive explosion occurred in cosmology. This result may represent supernovas, which may produce vast low density volumes. Now dig this. Are we getting the universe that we actually have just from the equations and postulates of binary mechanics? It's starting to look that way. Volumes with very low energy density are opaque to light transmission. I mean, you could just slap me in the face for saying that, but I said that as predicted, I think back in, more than 15 years ago, or maybe 14, 15 years ago, and as demonstrated. Why would this happen? Any incoming quanta to these low density volumes would be captured in electron and proton bit cycles before any of that energy can make its way through that volume to be seen or detected on the other side. That's a unique prediction of binary mechanics. So we have this, what is it called? The Oort void, or there's these huge cosmic voids out there. A unique prediction of binary mechanics that gives us, now, if you were just to dream up a universe, it wouldn't necessarily, from some theory, it wouldn't necessarily be the one that we actually have. It's starting to look like binary mechanics might be unique in giving us the universe that we actually have. In some, there's a balance between energy aggregation due to the motion law and various explosions or massive jets of quanta and perhaps other phenomena that we don't, I don't know about, from highly energy dense volumes, such as near galactic centers. Now, this is really getting, we're almost to happy time. We're well on the way to making a pretty good universe. Energy density thresholds. Elementary particle formation requires a minimum threshold energy density. And here we see, if we break it down for getting a proton, it's about 0.07, less than 0.1. You can see the little dots are above. If we magnify just this area here, which I did in, which you'll see in the next figure, you'll see that there's a definite threshold for creating a proton. The figure 9 plots the proton count after cooling as a function of initial density. In the experiment shown in figure 8, the one about the explosions and vacuum content, with the explosions that occur at very high energy density, the number of protons resulting in the volume when it finally cools down are few compared to lower initial energy densities. Okay, elementary particle formation. How do we get these elementary particles? Well, we need to know that if we're going to have any kind of a decent cosmology, right? The time development laws of binary mechanics, which happen to be these equations, I know that's going to sound cryptic, but you can look up the references, what these equations are saying, result in creation of 8 elementary particles. By creation, we mean that the random distribution of quanta with which we can seed a simulated volume to begin a simulation, that this random distribution is organized by action of the binary mechanic equations such that after cooling, the one states aggregate to form 8 elementary particles as predicted way back in 2010 in table 1. And this table 1 is also repeated in the paper Binary Mechanics Postulates. The vacuum mode producing cooling, in other words, was used to observe ground state particle composition. And only with the binary mechanics lab simulator can you really truly observe ground state particle composition. Because anything we do here on the surface of planet Earth, or if we dig a hole in planet Earth or wherever, or even on a satellite out in space near the Earth, it's in motion. So we're not going to ever see what the ground state actually is. So this is the first time ever you're ever going to see what the particle composition is in their ground states. Now, what is this mysterious figure? What if I click on it so you see the whole thing? Okay. In this figure shows spots with 3 one-state quanta. In other words, the energy is 3. And as we know, each spot unit contains an M and an L location. And there are 3 spot units, which can be shown in this column here, and they could have these configurations. These are the possible permutations of energy level 3 in a spot, consisting of 3 spot units. When we cool down to 0, and here's the random distribution, the probability of seeing any particular pattern shown in this figure. The totally astounding results, and I say astounding almost as a spectator. Yeah, I wrote the software and ran these analysis programs, but I was not expecting this. I was knocked to the floor practically to see these results. This is totally astounding that the equations alone in the simulator organize the quanta in patterns which correspond to 8 elementary particles shown in green highlight here. And these 8 elementary particles have more than a 20x higher probability of occurring. See, 0.13 is more than 20 times the random expectation phenomena. And you can get out your statistics equations and calculate the P level for that. Don't even bother. It's near 0 that would happen by chance, especially in 8 particles. And not only that, the 8 particles predicted by binary mechanics spot cube latest model. So here we have the left-handed, which are antimatter, red, green, and blue d quarks appearing after cooling. And you see there's no inertia. Inertia is defined in the laws of motion, which I referenced. I didn't explain in detail, but I referenced above. Anyway, here we have the right-handed blue, green, and red D or down quarks. Their probabilities after cooling to 0, that means ground state. And here we have the positron, which is, again, 3L type quanta, and the electron, which is a 3M type quanta. In other words, the positron and the electron are not exactly opposite as current conventional particle physics would have us believe, that antimatter is exactly the same as matter. And you can also see that the composition here in the comments for the matter particles here, the matter quarks, I should say, is different than the composition for the antimatter d quarks. Okay, let's see if I can get back to the text here. So this was an astounding result. I said, so I had to say, someone must be playing games with my mind or something. This is almost too good to be true. Okay, figure 10 represents the states, as I've explained here. I think I've covered all of these points. 20 times more likely, you see here, than expected by chance alone. This similar aggregation produced 2 leptons and the quarks, and completing the list of 8 elementary particles predicted by the binary mechanics system state equations. These results are stunning, as I've said. I'm saying this almost as an observer. I myself was stunned. I said, there must be some mistake. you won't believe the amount of time I spent. There's something wrong with the program. I have a variable mixed up somewhere or whatever, and how much time I spent trying to find a mistake in the software. At 0 Kelvin, possible with the binary mechanics simulator, there are zero net particle motion, and this is an important point. Although one states continue to move in their proton or electron bit cycles, this might be a source of 0-point energy. In other words, even at 0 Kelvin, according to binary mechanics, a lot is going on. The bits that are there, but below particle threshold, are still moving around in their bit cycles. Yet considering all possible states with energy 3 in figure 10, all the energy is confined to only 8 configurations. And this is repeating what I've already said, so I'll skip down. In sum, we now know a lot more about how particles exist in our universe. That's, I'd say, a big step in creating a cosmology. We know how we get these particles. By the way, these 8 elementary particles are recognized in the standard model. The original 2010 binary mechanics paper itemized how combinations of these 8 account for the 3 generations of the standard model particles. So if you look at the standard model, and they show this nice picture with this square filled with the different particles, and there's 3 generations of them, and the Higgs boson is usually shown off to the side. But in this square, there are 3 generations. All of the other particles really can be seen as compositions of the 8 particles defined by the binary mechanics spot cube. Now, I mentioned I would talk about particle thresholds and zoom in on the picture I showed above, the data I showed above. The time development laws also determine the minimum energy density required, or threshold, for formation of each of these particle types. How much energy do you need? Well, this figure shows that information. And you notice that around what we have here is 4 different bit operations, which is the scalar, unconditional, vector, and strong, which I'm not defining here in this talk, but they're in equations 7 through 17. And their equation 17 specifically has to do with applying these 4-bit operations in different orders. And you notice that one of the orders, you get different results with different orders. So one of the results is that the SUVF order is the one that creates the most matter d quarks, right-handed d quarks. And here is the EXP is expected by chance alone. And so these results are far away from what you get from chance alone. So again, the P, you don't even have to state how many sigmas of significance you have here. It's maybe a dozen or more. This is hugely significant results. And so what this figure shows is that it does matter what the order of the bit operations applied. Yes. Hello. Yes.
Oh, whatever you want. Okay.
Oh, okay. Let me continue. Technically speaking, the bit operation order does not commute, as you saw in the figure above. That is, different orders produce different results. Thus, one and only one bit operation order in equation 17 can be physically correct. The one point to take home is that the universe runs by applying equation 17 repeatedly in what programmers might call a loop. So far, we now have the universe up and running. Okay, so this is a major point in our universe here, to get it up and running, and now we're up and running. Hallelujah. Nucleogenesis, the proton or hadron bit cycles. Why do we call it the hadron? Because it's actually a whole family of particles. But we just, for simplicity, going to call it the proton bit cycle. Aggregates one states in adjacent spot cubes, as I described above. This is a foundational principle in nucleogenesis in nuclear physics. To summarize, each spot cube can be designated as home for a proton, electron, or both, a neutron. That is, a nucleon, proton, or neutron is associated with a spot cube, as shown here. On the left side, we see what I already showed you in the proton bit cycle detailed or so-called pro version of it, showing that off to the lower left and lower right and up above, there were extensions, or the proton bit cycle actually moved into the spot cube above or to the lower left, or the spot cube to the lower right. Now let's consider this side, because we need all 6 directions. Figure 5 showed the 42 loci in the proton bit cycle. And we defined the home spot cube as I mentioned. Now, figure 5 also showed that a nucleon bit cycle does not include quanta traffic in the positron spot in its home spot cube. Now, if we go back, let's click on this and see if we can go back. I don't want to mess this up. Let's see if I can get, how do I get back? Yeah. Okay, you notice that in the home spot cube of this proton bit cycle, its positron, which exists in this spot cube, and the electron, by the way, is empty. If we add an electron, as I said in the text, you'll get a neutron. But what about this empty positron spot? In other words, in the home spot cube for a proton, the positron spot is not used at all. It's not included. Where does positron spot units occur? They occur in these extensions, the gray ones, here and here and here. Okay, let's see if we go back now to the text. Okay, so this is what we mean when we say that it does not include quanta traffic in the positron spot in its home spot cube. I just tried to show you that. What might this home spot cube positron spot do? What is it there for? Each spot unit in this home spot cube positron spot is part of the proton bit cycles in 3 neighboring spot cubes. Yeah, okay, that makes sense. I now see how all that is linked together. This connectivity is illustrated by the arrows in figure 12 right. Here, our positron shown in gray. And so now we have arrows of connectivity in the spot cube lattice. Very important for nucleogenesis. Now, each spot cube is part of in other words, each spot cube is part of what we might call a proton cycle network, connecting it to 6 adjacent spot cubes. The function of the spot cube cycle network is atom and isotope formation, such as presented in the periodic table of elements. How would this work? If the number of quanta, energy quanta, by the way, that's redundant. You know, if you understand how I'm using these terms, that's actually redundant. But we're allowing a little redundancy here just because we're trying to get our message across. If the number of energy quanta increases in a proton bit cycle, where might they go? Not just anywhere. The proton cycle network indicates the most likely outcome, namely dispersion of quanta to neighboring spot cubes, resulting in generation of objects with higher nucleon count and atomic number. This is a foundational principle in nuclear physics, and no doubt future nuclear physics books might well start with this phenomena. Now you can tell by the cursor here are the indicator here in the scroll bar that we're almost done here. Hallelujah. Okay. Here's what I wanted Ito to see. Periodic table of elements. Figure 13 shows electron-proton distance. How do we get this? Well, when you run the simulator, it outputs files with all of this information. And it gives you the positions of the protons and the electrons, and then you can calculate from that in a spreadsheet. You can load that into your spreadsheet program and then calculate proton-electron distance as a function of energy density. From absolute vacuum, shown at the left here, and defined as 0, 1 states. Okay, in other words, partial or perfect vacuum, as we saw in the figure above, is teeming with 1 states. It's far from perfect in terms of what people were saying, thinking that, well, that space is empty. Well, it's perfectly full of quanta is what it is. So if there are no quanta, we have to use a different term, and we call it absolute vacuum. Up to the maximum where every locus is in the 1 state over here. So let's scroll down so you see the whole thing. Okay, great. You notice that we have the proton threshold is about here. It's less than 0.1 on our energy density scale. And here we start to get our first protons and hence our first hydrogen. And it's a little bit later, you got to increase the density. So we have a higher threshold for the first neutrons, okay? And so we're probably getting some higher Z atoms starting to form here. Now you notice as we continue increasing energy density, it looks like a stair step going down. If this were truly random, you shouldn't see a stair step. This is the point that I think supports Cal's model, okay? If this were random, I couldn't say this, but it's not random. You have a stair step. It looks like perhaps objects of a certain number of nucleons are forming and adding up there. And so then we go boop, down another step. And then we get another step and then another step, as if there is a non-random formation of higher Z atomic number elements in the periodic table, okay? So that's what this is showing. And we're almost down to the end, which I'm so happy because this is a pretty good universe that we're getting here. Very low energy densities below the proton and hydrogen threshold may be characterized as an electron gas in perfect vacuum. Above the proton threshold, a neutron threshold may be defined, as I said. The electron spot in a proton home spot cube is not part of the proton bit cycle. You notice that in the previous figure 5. Indeed, the electron spot has its own bit cycle, as we've seen. If 3 M-type quanta make their way into that spot, a neutron is formed. This event has its own higher threshold, as we've seen in the data I have presented. At about 0.14 energy density, the dip in the proton-electron plot is thought to indicate increased neutron abundance as nuclei with more neutrons and higher Z elements are formed. Higher Z atomic number are generated as energy density was increased to about 0.6 maximum, completing the periodic table of elements. Amazing stair-step decrease in observed proton-electron distance may reveal, this is the sentence for Ito. Amazing stair-step decrease in observed proton-electron distance may reveal non-random structuring of the geometric arrangement of nucleons in nuclei as heavier elements are generated. This observation, I think, generally supports Ito's work. Above about 0.6 energy density in the range labeled plasma in figure 13, plasma should be considered here basically as a label, okay? And the dramatic increase in proton-electron distance may indicate that ionization becomes predominant. right here. You see the dramatic increase in proton electron distance. Okay. Of course, this does not exclude ionization events at substantially lower energy densities, all right? Finally, above the 0.75 energy density lepton quark soup occurs, where individual particles such as protons and electrons are not clearly definable in such extremely high energy volumes. As previously reported, this high energy range is called lepton quark soup because the quantity of leptons is greater than quarks, and that's documented in this reference. CERN researchers do not appear to have much of a good idea of what they're doing. This is a whole big topic right there. They named this a quark gluon soup, but this is mistaken. By the way, they talk about proton-proton collisions and as what they are studying in multi-million-dollar research NSF grants to be done on colliders such as at CERN, up to 13 TeV energies. While it is likely that these are really soup beams that they are colliding, not actual specifically definable protons. This shows you how far behind CERN is. If you look at binary mechanics, they're so far behind, they're like in the Stone Age. With the foregoing aggregation events producing atoms in the periodic table of elements, we have gone a long way toward a very interesting universe. A further major aggregation step is formation of molecules. I'll leave that to the chemists. They've done well in describing processes of molecule formation. Life. Next, biologists and biochemists added shock and awe to our universe with huge, and thank you for that, with huge molecules in DNA and proteins. Starting with the spot unit in binary mechanics, not only may a universe be created, it can also be populated with living organisms. So to go back to my introduction, the first paragraph of this talk, you have to start with the best theory of everything in order to get everything in the universe. Start with the best theory of everything and get the best cosmological model. Without a good theory or the best theory of everything, you're really trying to climb a mountain to do anything useful or viable in cosmology. Build from binary mechanics full quantization postulates and devices called spot units and get everything in a wonderful universe. A couple of brief points.
All right, I think we're going to get cut off. Coming to the end.
Okay, the first point in the discussion, maybe there's time for that. Notice that all the aggregation steps described involve collection of energy quanta into smaller volumes. Not only does this sound like gravity, these aggregation events define gravitational phenomena. Therefore, binary mechanics equations, which demonstrably produce aggregation events, provide the best mathematical model for these phenomena. Rigorous applications of the scientific method is superior to blind guesswork in discussing gravity. And day and night, this is just a general summary, maybe we'll get cut off. Binary mechanics replace the theory of space and time are continuous, which has guided science for millennia. Binary mechanics.
Well, I see we have Roger here now. All right. You did get cut off. There was a weird thing happened there in that it didn't give a 10-minute warning. And I thought maybe it might continue on past the 40 minutes, but it didn't.
Okay, well, I just have one short paragraph of discussion related to the presentation, and which will take just a minute or so, but I've requested to share screen because if there's any discussion of what I presented, we might want to refer back to some of the illustrations.
Okay, go ahead, finish it up quickly.
Okay, thank you, Harry. So the basic context of this presentation is the major difference in the fundamental axioms of the binary mechanic version of the universe and really all other theories that are popular in physics today are presented, even if they're not popular. Binary mechanics replaced the theory of space and time are continuous, which is guided science for millennia, and this characterizes, general relativity, standard model. I mean, special relativity. All of these are based upon this axiom that space and time are continuous. Binary mechanics just departed from that, and there's a reason for that, which I've given in other presentations. And it postulated full quantization of space, time, and energy. As a consequence, the equations provided a new definition of system state and time evolution. And those are the two things you need to define any theory of everything or any theory of physics. Just two things. You don't need any other fluff or icing on the cake. You just define your system state and how it evolves or changes with time, and you're done. That's it. In addition, this article presented how these equations produce a fully functional universe. And not just any universe, the data indicated that binary mechanics generated the specific universe that we have. Now, what are the odds of that? This is the road to the best cosmological model possible. All other efforts in theoretical physics continue to embrace the outdated theory of continuous space and time. To make matters worse, most investigators agree that these efforts are incomplete. This is not what I'm saying. This is what the majority of physicists and astrophysicists say. They just are completely ready to admit that the models that they are using are incomplete, whether it be the standard model, quantum mechanics, special relativity, or general relativity, among many other serious defects, which I pointed out in this publication. Therefore, some strive to combine or unify these approaches in apparent endless hope of violating the two wrongs don't make a right rule. You see, like if you got two theories which are faulty, but we can combine them and make a good theory, that would be violating the two wrongs don't make a right rule, which is, a rule which, according to my mother, at least, bless her soul, she's now departed, is a very important rule. The worst problem of all for the incomplete theories is that the sun rises every morning. That is the big problem. That is, as far as is known, the universe is up and running as we speak now. This observation is a daily reminder to the proponents of these failing theories that a new approach with different axioms or postulates, with such as full quantization in binary mechanics, may be required to achieve a minimally acceptable understanding of how the universe works. And thanks for your attention. And if we want to refer to any of the figures above, I have the screen sharing going and we can do that. Thank you for the opportunity to talk with you.
Okay, Jim. Well, I see that you've made some changes. A lot of the structure of this is pretty much the same as you presented before, but you've given a more cosmologically oriented take on it. Is that correct?
I think so, yes.
So you've tried to.
And I have to thank Mr. Harry Richter, or Dr. Harry Richter, whatever it is. Sir Harry Richter. Because without these cosmology sessions, I wouldn't have even thought about what implications binary mechanics has in cosmological modeling. So thanks to you for having these sessions. You started me thinking in that direction, sir.
Well, that was one of the reasons for doing this, is to, that's why it's called a discussion group, isn't it? We're talking about cosmology and ideas associated with that. The idea of cosmology and how the universe works. Okay. Do we have any questions? I'll open up to the discussion for questions, and if nobody has any questions, I'll start off with some comments.
One question. That graph that's shown here right now, that's where I had to pay attention, I think. I'm happy that the correlation is made there, or that it shows, that there is an underlying organization, if you will. And of course, if you shoot that kind of information to me, I go like, well, yeah, duh. There's a whole set of rules and logic and etc. And we wrote a whole book about it. So I'm really happy that you found that. The question would be, is this a strictly theoretical model? And this graph that I'm seeing with these electron-proton distances, is that a practical result, or does it come out of the model as well? And then the second question would be, can you do it without antimatter?
Well, the model includes all locations in the spot cube, and notice in the spot cube and the proton bit cycle, the matter and antimatter quarks are included in the and also the positron, which is antimatter, conventional classifications, are included in the proton bit cycles. Now, another thing that I'm noticing, and to answer the question further, this graph was generated by doing one of the experiments in binary mechanics lab simulator that you're allowed to do. And if you press the help button while it's running, it will show you, what explain that in more detail, or read some of the papers that indicate what experiment was used. So this data is from the simulator, and it specifically started with an empty or near empty volume of simulated space, and incrementally added randomly quanta to gradually each dot in here in the plot. It indicates an increment on the way to 100% 100% density, okay? Maximal density, which is a new concept in binary mechanics. It's in particle physics.
But this would be an essentially cubical system then, visually at least, and
yes,
perhaps dimensionally.
Yes, it's a cubical system.
Okay.
So one thing I'm noticing right now, which may be of interest to Ito's thinking, is that you notice that the length of these steps is different. Here's one with a shorter length, if you can see the hand cursor. Here's one with a longer length, which is similar in length to this step. And this seems to be a short step here again. And so the length of these steps, as we're creating the periodic table moving on up, is different. And it's indicating to me, the reason why I think it supports your approach, Ito, is that it indicates that this is not a random process. And that's the whole basis of your model, your SAM model, that it's not random, that there are groupings which occur, and it could be this is depicting the exact groupings that you are actually talking about.
I'm not able to make it from this quick and dirty debate we're having here, of course, but what I can say is, and that's what the book is all about and presentations are about, is that there are many recurring regularities, but the periodic table is a very nasty thing, because every pattern we think we can let loose on it, like, something like a formula, like the cycle of 8, the oxidation value, or the valence value, if you will. It goes from 1 to 8, and it repeats, but it does break. Every pattern breaks, and perhaps complexity organized complexity always comes out of a simple starting point. I guess is what I'm referring to. Hence my cubical comment, because I have a spherical environment, if you will. So you get a
Yeah,
different
your
pattern.
model is in in continuous space and time, I guess. You're using the conventional physics theory, and you know, all I can do is to suggest to you to look into an alternative approach, such as binary mechanics postulates presents, because all of these continuous space and time models have failed to derive the fundamental constants of nature, the speed of light, electron rest mass, Planck's constant. You
Well,
see,
see,
the
that's where
first
you
thing I did with the proton bit cycle
right.
was to derive Planck's constant.
This is where you catch my attention for sure, because it's something that I'm very much looking into and alluded to when I did my presentation with the mass of the neutron and the most simplistic fusion fission process, meaning, you know, putting a deuteron together and ripping it apart again, which is, you know, just the example for all the other processes. And I'm looking very much at coming up with nature's standards, if you will, from first principle, I think is the terminology here indeed. And so I'm looking at, for example, the charge distribution, or I should say the virtual charge distribution of a spherical object. So we can resolve the point particle issue there. Because the point particle at a quantum scale, if you go to a wiki, Coulomb calculations, you refer to that, right? With attracting, repelling forces, calculations, etc. Distances between protons and electrons or similar. If we do the Coulomb calculations, allegedly it breaks down at the quantum scale. But I believe we can resolve that, and that's something that I'm working on too. So I think we should just definitely have a chat about this at some point in time. So you caught my
Well,
attention.
I would most welcome that. Now, with the proton bit cycle having 2 to the 42, 2 raised to the 42 possible patterns of one states distributed in the locations, the loci in that cycle, the amount of complexity is enormous. So I'm not surprised when you say that various simplest, you didn't use the word simplistic, but the various rules which you have explored are can be violated or not apply. And what I can say is that I think this approach, you know, is actually useful to determine a lot of things that otherwise would remain hidden to our awareness.
Right, right. So the comment that I would like to make as a point of criticism, if I may allow myself that,
Yes.
I am a firm believer, and I choose that word on purpose here. I do not believe in the concept, the entire concept of antimatter. I do not know if you are adamant about that, that it must exist, or that there's a possibility of looking at something like this model that you've explained today without the concept of antimatter. Is that even a viable thing in your mind, or am I saying things now that you go like, shh, go away?
No, I mean, the I in the development of binary mechanics, if one wants to torture oneself and read all the papers from the beginning to the present, I've used a lot of terms which are prevalent in physics, such as antimatter,
Mhm.
to try to relate to the thinking of the reader or of likely readers of my publications.
Right.
But as I pointed out today, the concept of antimatter in current particle physics in the mainstream is broken by binary mechanics. You see, the electron has its bit cycle, but the positron, the so-called antimatter equivalent to it, is not does not have a bit cycle, and it behaves entirely differently, as we've seen in the illustrations that I've shown. So that I think your comment just a moment ago helps me to better understand that there's a real risk in using terms that other physicists and particle physicists use when in fact they don't really apply fully
Right.
to binary
That
mechanics.
is.
Like if I had labeled the 8 particles 1 to 8, you know,
Then I would never have posed my question, even for starters, right? You would have simply used different terms and etc. there. The only reason I respond to that from antimatter is because it is one of the pillars in the standard model, indeed. And and this is simply from my own observation, from my own truth. Yeah, I make no other claims than that, but through my own investigations and research, including looking at the standard model, the concept of antimatter to me, in the end, is quite silly. It's not realistic, and there's a chance, at the very least, if we're objective, that the whole concept is simply wrong, right? It was at one point in time postulated for some specific reasons, and I'm not saying that's a wrong thing to do, even.
well, you
But
can
if you base your
cite
model on these concepts, then yeah, then there's there's a risk there.
exactly, and your comment there is greatly appreciated. It's going to make me a lot more aware. Like, for example, the antimatter particles, the left-handed d quarks here, this group of 3 highlighted in green, have a different composition, 1m and 2l type quanta for a total energy of 3, whereas the so-called matter right-handed d or down quarks have 2m and 1l. So you see the right there, binary mechanics is contradicting the idea that antimatter is just simply flipping in the reverse everything that you have
Right,
in
the opposite
matter.
of,
The
yeah.
same way with the positron spot here, 3 L's type quanta, and the electron is 3 M's. And by the way, the electron can combine with the proton to make the neutron, but the positron can't combine with the proton to create whatever. So
Right.
at least so that really binary mechanics, no matter what you look at, contradicts the idea that the so-called antimatter particle is just the inverse of the matter particle in all properties, including its composition, as shown in the comment column here, as well as its properties are different. So that on both counts of composition and particle properties, they're different. And so again, I guess you pointed out the flaw, because people are going to think, like, for example, I've seen in the recent press that people are trying to find out whether the antimatter version of hydrogen or whatever is actually exactly the inverse in all respects, in how it responds to an electric field, et cetera. And people are really wondering about whether that idea that the antimatter particle is everything is just opposite from the matter particle. Well, binary mechanics says no, that's not true. And so maybe the whole idea of me using that term is I'm shooting myself in the foot. You
Well,
see what I'm saying?
I'm
If
not
I'm
going to be
saying,
the
well, you
judge on
see, the
that one, but
positron is our
right.
antimatter particle, I'm shooting myself in the foot, because everyone's going to think, oh, it must have opposite composition. And I mean, it must be in all respects the opposite of the electron. But I've shown that it's in all respects not the opposite. It's different from the electron.
Right.
Thank you,
Okay.
Edo. That is
Well,
very important.
thank you for your explanation there. Thank you.
Okay, anybody else with any comments or questions? Gonna get dead silence here.
Well, I've got one more
Okay.
then. I've got one
I
more.
might make a general comment, which is a bit of a critique on the whole system, I suppose, Jim. I think at an earlier stage you intimated to us the genesis of this. If I recall correctly, you were sitting in a kitchen with some colleague or something, and he gave you some ideas which you pursued subsequently. But anyway, you can maybe remind us of that. It seemed to me that from these ideas, it's almost like a bit of a series of thought experiments that led you to these concepts. And then, to use your own words, the results are too good to be true. I mean, it's so remarkable that everything in this concept seems to accord with the universe that we have now. And you have said yourself, indeed, today that you have spent numerous hours trying to establish where there might be some discrepancy, and you couldn't. So I suppose that's a general concept. I'd also like to see a bit more, rather than accordance with the observable universe, the macroscopic universe, maybe some detailed experimental results, contrasting with those results compared to existing theory, existing cosmology, which I think most of us here anyway do decry, but we would do so for different reasons, perhaps, than what you might, Jim. So that's just a general comment. I hope it's not too critical, but there you go.
No, actually, Ian, it's a welcome comment, and I think what you've described is pretty accurate. That I would actually agree with. The basic point that James Hughes was the one who got me started on this. He pointed out that rotating the spinner, the Pauli spinner matrices, resulted in each one giving a 0 or 1 result. And most physicists agree that if you rotate a matrix, it shouldn't change the physics. It's just changing the way you're looking at it. And so when Hughes presented to me in my kitchen, as you mentioned, as a starting point, that a simple rotation of these matrices, which is covered in my very first paper, of my version of how you could rotate them so that they produce a 0 or 1. And now take into account that each of these 3 spinner matrices is linked to a particular X, Y, and Z dimension of space. Okay. So in other words, considering that plus the 0 or 1 result gives you what? It gives you a cube. And so my very first question, so in other words, the real meaning or heuristic value, you might say, of the spinner matrices appears to be hidden in the fact that nobody rotated them in the way Hughes did to determine that this cube is defined by them and is required to get the results that conventional quantum mechanics comes up with, which have shown to be very accurate results concerning, let's say, electron behavior. So the very first question that I had is, well, what is the size of this cube? If you're saying that space has some kind of a structure based upon this cube, which seems to be so successful in quantum mechanics, although nobody knows it because they're using the unrotated version of the spinners. with the imaginary number in there and so forth. The existence of such a cube as being vital to the success of the Schrodinger co-equation was unknown. And so Hughes revealed this to me, and I immediately asked, well, what the size of this cube is. I mean, wouldn't we want to know that? I mean, that would seem to be an extremely important parameter. So anyway, I agree with Ian's view that going from this and then writing the software for the simulator over a number of years and doing these experiments and data analyses such as I have presented today, a lot of it could be considered, yes, as thought experiments. However, computer simulations are used widely in physics and astrophysics. And I mean, when you talk to an astronomer and they have something to tell you, probably the first words out of their mouth is, according to our computer simulation, the result should be X, Y, or Z. And, you know, so the fact that computer simulation is used is very much mainstream in both physics and astronomy in these days. So in general, I agree with the drift of Ian's comments. Now, what I have also done to supplement the simulations that I presented is taking other people's data, which you can download on the internet, concerning lunar laser ranging and the GRACE, GRACE, pair of satellites, which is based upon special relativity, and showing that their data actually demonstrates the Keene law of motion quite clearly. And so this is, you know, you could, you know, so for the part of Ian's comments of where's the real world stuff, well, those are two examples which I've published showing that the predictions of binary mechanics are borne out in the real world.
Well, thank you very much for that background. Actually, I hope I haven't missed anything, but it might be interesting at some stage in the future to concentrate a bit more on those two experiments that you talked about, maybe at a future presentation, which you might
Well,
give.
I would be glad to, because they both have to do with cosmology and the whole topic of gravity. And sure, you know, like I would be happy just to focus on those two, and it would be a much shorter presentation than today. I didn't practice today's presentation, so I wasn't sure how long it would take. I apologize that it took so long.
No, thank you.
It was a good one, James. Thank you very much.
Okay,
Can I
so I
ask you
guess
the question?
oh, go ahead.
Okay, as we know, physics is experimental science. Astronomers, they measured some very important parameters of our cosmology, like temperature of microwave background radiation, concentration of intergalactic plasma, Hubble constant, and all this stuff. Can you calculate, in frames of your theory, calculate all these well-known experimental results of astronomers?
Well, I suppose they all should be calculated or calculable.
What
So if you're
about
asking,
your
is it
calculations?
possible
I'm asking
to
personally
calculate?
your calculations.
Well, I mean, it doesn't matter who does the calculation. The generic answer to the question is whoever does it. I'm saying that all of those calculations can't be excluded as impossible. And in other words, they are possible. Perhaps
You
you'll
know, any might be in frames of a different series, different models, and so on. Particular in your theory, in your model. Man, it's possible. I calculated all these numbers, but I want to know, can you calculate in frames of your theory?
Well, what I can do is so far unknown. I can't predict the future.
Not the future, but the past results experimental. It's not future. It's what we have right now. Temperature
Well,
of
I
microwave
presented,
background radiation.
I presented what we have right now in 14 different illustrations.
Okay, let me interrupt here. We're coming up towards the end. I think what Vladimir is basically saying is what you don't really have a cosmology in the sense that in a traditional sense that you would find in a textbook that says textbook of cosmology. I have several of them. They're all based on general relativity. You're starting from a different point of view, I think. You're starting from the bottom and trying to work up. And modern cosmology kind of starts at the top and tries to work down, I think. I'm not sure that's a good way of discussing it. But
I think that's a fair description, Harry.
yeah, you've gotten to some big points. You've talked about nucleosynthesis, and you have a law, a kind of a law of gravitation, I think, a motion law, as you're talking about. You don't have like a theory of the universe in the grand full scale as per general relativity. I think and so you're not really predicting cosmic microwave background radiation, things like that.
Well, there's, of course, there's the spot cube lattice model includes the entire universe, whatever the extent of that is, and it certainly includes objects above 0 Kelvin emitting radiation. And so that, yes, my model does cover the cosmic radiation background.
Well, I think basically, from my point of view, what I would say is that I guess I'm sort of, what Vladimir would like for you to do is to give a prediction of the temperature of the microwave background radiation based on your spot cube model. I think that's what he's asking for.
Yes,
Is
Well,
that
yes.
correct?
maybe that will happen in the future.
And not only this one, but concentration of intergalactic plasma, Hubble constant, and all these well-known observational parameters, measured parameters.
Well,
Let me tell you my opinion, Jim.
there's no reason
Many
where I
times
should
I
do
told
this. Any person
one,
can do
sorry,
it.
let me finish.
Sure.
Many times I told you that I like your theory as a basis for quantum physics. You're trying to connect proton, electron, and all this stuff. It's okay. I don't mind, because in quantum physics there is a problem right now too. It is in crisis. That's why if you pretend to be a developer of quantum physics, well, it's okay. For me, it's fine. But as you jumped from your atoms, protons, electrons to superclusters, to some macro objects, huge one, it was unexpectedly for me. Because as you know, classical physics, in my point of view, it's not your cubes. It is ensemble of these cubes. It's a totally different physics, totally different story. That's why, as quantum physics, I do like your approach, continue, do whatever you want. But please don't jump to cosmology, because for me, there is no correlation between your theory and cosmology. Sorry.
I would like to say that most of us here don't really accept the standard model. I know that Harry is a believer that the CMB is a local phenomena, maybe not from the Earth itself, but from the galaxy that we exist in. The the question of redshift is up in the air since the discovery of Halton Arp of these quasars that are being birthed out of galaxies that are way less redshifted, and they're actually been they have physical connections between that less redshifted galaxy than the quasar that they're measuring. There's a physical
Okay.
bridge of
We have
plasma
not so much
between
time
them.
left. I ask you the same question?
I'm just saying
On
standard
your
model
theory,
is in question. That's all.
okay, based on your theory, can you calculate temperature of microwave background radiation, concentration of intergalactic plasma, and Hubble oh my goodness, Hubble
Tension.
constant, because for me, Hubble parameter, that's why. Please, do you have these calculations based on your model? Guys, we are in business of experiments and correlation between theory and results of observation. Do you have in your plasma physics, in plasma cosmology, these numbers calculated in frames of your theory? Do you?
Not at present, no.
I mean, not you, but plasma physics. I'm tired of all these words about plasma physics. If you have your plasma, please calculate the parameters well known, experimentally observed, confirmed. Please calculate it.
Well,
Because to talk about
you're asking
physics
me to
in words, it's one story, but in numbers, it's another story.
You're asking for calculations that are not necessary. Because if in fact the CMB is a local phenomena,
Don't care. It's a physics. Local, not local. It's your opinion because you have the different story. But do you have
well,
any
they measure
number
the CMB.
calculated based on your theory?
They measure the CMB based on a flawed theory that they think that the universe exploded into existence 12 billion years ago or 14 billion years ago or whatever it was. That's wrong.
Guys.
That's
Okay,
wrong.
all right. Let me just say here. I think what Vladimir is saying is he's saying that if Jim, if you're talking about cosmology and binary mechanics, he's asking you to deal with the classical issues in cosmology, and those classical issues are what is the source of the CMB? What is the cosmic medium? What is this cosmic medium? Does it exist? Does it not exist? Does your model allow that or predict that? Can you predict the Hubble constant? Can you explain whether the universe is expanding or not? These are the classical issues in cosmology that they talk about in textbooks. And you're not really dealing with that. You're dealing with a ground up, starting at the elementary particle level and trying to build up a universe from that. And it's really not quite there yet. I think that's what Vladimir is saying.
You're absolutely right, sir. I'm happy that you understood my concern about this jump from elementary particles to macrostructures. It's too far. I'm sorry.
Question. The CMB, is that considered a remnant only from the Big Bang? Or, and this is my own thinking about the cosmological topic and nucleosynthesis, if the universe started from primordial protons, electrons, if you will, then the amount of fusion should be connected to the total